Assalamualaikum and good day everyone. My name is Amza Yusri, a member of Group 23, and today I will be presenting about our key findings of our project titled as Analysis and Design Improvement of Human Prosthetic Leg along with my group members. Let's begin. Before we begin, let's meet the group. As I mentioned earlier, my name is Amza Yusri and I'll be the one that in charge on handling the CAD modeling by designing the ideal prosthetic leg with precise dimension. On the other hand, we got our second member, which is Adam Akmal, and he is the one that conducted the analysis of the product using the ANSYS Workbench software. And the last member, we got Nur Nadia. She will be the one that in charge with technical writing, as she will document every report, every findings and the results throughout the process of this experiment.
My name is Nurnadia binti Muhammad Talas. So today I will introduce our project, which is Prosthetic Leg. This project focuses on the design improvement and performance analysis of a human prosthetic leg. A 3D model of the prosthetic leg will be developed using CATIA V5, followed by structural analysis using ANSYS to evaluate its strengths, deformation and overall performance under loading conditions. The analysis result will be used to identify weakness in the existing design and propose improvement to enhance functionality, durability, user comfort and safety. So for our objective is, first we have to design a complete 3D model of a prosthetic leg using CATIA V5. Second, simulate real-life loading condition using ANSYS. Third, analyze stress distribution, deformation and factor of safety. Fourth, we have to identify critical errors that may cause failure or discomfort. Lastly, we have to propose design improvement to enhance strength, stability and usability.
Next is project scope from concept to implementation. Firstly, research existing prosthetic leg design. The first scope of this project was to study existing prosthetic leg design. We reviewed different types of prosthetic legs currently used in the medical field and the research study of the prosthetic leg to understand their structure, material advantage and limitation. This research helps us develop a different design that is both strong and lightweight. Next is create individual components and assemble them in CATIA V5. All the parts and components of the prosthetic leg were designed using CATIA V5. After creating each part, they were assembled to ensure that every component fitted correctly and functioned as a complete prosthetic leg. Next is we assign appropriate material properties. After completing the CAD model, suitable material properties were assigned to the prosthetic leg. In this project, different engineering materials were considered to evaluate their strength, stiffness, and suitable for prosthetic application. So we find some suitable material in the current research study for the prosthetic leg used, such as aluminum alloy, titanium alloy, carbon fiber, and others. Next is import the model into ANSYS for final element analysis. The completed CATIA model was then import into ANSYS Workbench. Final element analysis was performed to stimulate the mechanical behavior of the prosthetic leg without producing a physical prototype, which helped us save both time and cost before manufacture the real product. Next is apply boundary condition and loading scenarios. Boundary condition and loads of 1103.6 Newton were applied to represent the weight of a human body during standing, walking and others. The bottom of the prosthetic leg was fixed while an external load was applied to simulate the force experienced during normal use. Evaluate analysis result and compare the design. The simulation results were evaluated by analyzing the equivalent stress, total deformation, and safety factor (FOS). The original design was then compared with the improved design to determine which design provides the best structural performance while maintaining safety. This approach has produced a design that is safer, stronger, and more reliable while reducing development time and costs.
Okay, let's move on to the analysis result of original versus new material for improvement design number 1. Okay, so the purpose of this analysis was to identify the areas experiencing the highest stress and deformation. From the stimulation result, I found that the base of the prosthetic foot was the most critical component, despite experiencing the highest stress concentration, making it more likely to deform or fall under some repeated loading. Based on these findings, I decided to redesign the foot base to improve its mechanical performance. The new design features a modified geometry that helps distribute the applied load more evenly, which greatly reduces the stress concentration in critical areas. In addition to the geometry improvement, I selected a new height density material with better mechanical properties, height stiffness, compared to the original one. This material offers higher strength, greater durability, and also improved resistance to deformation, making it more or less to bend due to a high load applied, such as for humans with higher body weight. After completing the redesign model, I performed another structural analysis in ANSYS using the same loading conditions. The simulation result shows a significant improvement in the stress distribution and overall structural performance, which means the redesigned foot base experienced a lower maximum stress and reduced deformation, indicate that the new design is much more stronger and more durable than the original. Alright, so now let's talk about the numbers. The design improvement number 1 of the bottom foot plate experienced around 5.5 megapascal of stress compared to the original design, which suffers much more higher, which is around 15.5 megapascal. These numbers indicates that the design improvement number 1 perform much more better than the original design due to some factors which we consider, such as the material properties, the geometrical design, and much more.
Temperature difference for improvement 2, which focus on redesigning the lower pylon tube of the prosthetic leg. The objective of this improvement was to increase the strength of the lower pylon and improve its performance when exposed to different temperatures. In the original design, the lower pylon consisted of a single hollow tube which provided limited support. To improve its strength, I redesigned the lower pylon by adding support beams around the tube. These support beams help distribute the load more evenly and make the structure more stable. Besides changing the design, I also upgraded the material to titanium alloy because it has a high strength, excellent corrosion resistance, and good biocompatibility, making it a suitable material for prosthetic application. A thermal structure analysis was performed by applying a temperature of 80 degrees Celsius to evaluate the performance of the redesigned lower pylon under thermal loading. The topology optimization value remained the same at 0.66471 so that the effect of the new design and material could be evaluated fairly. Based on the results shown in Table 3, the equivalent stress is 3.664 megapascal, which is much lower than the original design. This indicates that the added support beam successfully reduced the stress by distributing the load more effectively throughout the structure. The total deformation is 1.1368 mm, although it is the highest deformation among the improved design. It is still relatively small and remains within a safe operating range. This suggests that the structure is slightly more flexible while still maintaining its strength. The factor of safety is 15, which indicates that the redesigned lower pylon is still structurally safe and capable of withstanding the applied loading conditions. Overall, the results show that the combination of the reinforced lower pylon design and the titanium alloy material improved the overall structural performance. The lower stress value indicates better load distribution, while the high factor of safety confirms that the design is reliable for long-term under temperature loading. In conclusion, Improvement 2 successfully achieved its objective by strengthening the lower pylon through the addition of support beams and the use of a strange material. The design provides better structural performance and is more suitable for prosthetic leg application. For the discussion, overall, the analysis showed that the design improvement reduced the equivalent stress by up to 76.34%, proving that the modified geometries distributed the applied load more efficiently than the original design. However, this also increased the total deformation by up to 179.04%, showing a trade-off between lower stress and stiffness. Improvement 2 achieved the lowest stress but had the highest deformation, while Improvement 3 provided a better balance by reducing stress while keeping deformation lower. Therefore, Improvement 3 is the most practical design as it offers a good balance of strength, stiffness, and safety, with all the design meeting the required factor of safety.
In conclusion, the objective of this study has been successfully achieved by designing a human prosthetic leg in CATIA software and evaluate it using the finite element analysis in ANSYS Workbench. The analysis assessed the equivalent von Mises stress, total deformation, strain distribution, and also factor of safety under the applied loading condition. Moving on to the improved design. The improved designs greatly reduce the equivalent stress compared to the main design, as the Improvement 1, Improvement 2 and Improvement 3 record a total of 5.52 megapascal, 3.664 megapascal and 3.362 megapascal respectively, compared to the 15.5 megapascal of the original design. However, this resulted in higher total deformation, showing a trade-off between reducing stress and maintaining stiffness. All design achieve a factor of safety of 15, confirming that they are structurally safe under the applied load. Overall, the result shows that the finite element analysis is also an effective method for improving the human prosthetic leg design before fabrication. So the Improvement 3 offers the best balance between stress reduction and stiffness. Also, the future work should focus on further optimizing the design for lower weight and better performance, as well also as validating the simulation result through physical prototyping testing. Alright, so that's all for me.